GTC, first and foremost, is our opportunity to highlight the amazing work that our engineers and our teams here at NVIDIA have done all year long. It's always been filled with the most amazing demos in deep learning, supercomputing, and computer graphics. What was different this time was that we used our own platform, Omniverse, to create the amazing visuals and demos for all aspects of the keynote.
Here it is.
Slides for any keynote presentation are critical. We use these visuals to convey extremely complex ideas to everyone. In the past, we used to use PowerPoint to create these slides. This year, our slides are virtual worlds, completely created and rendered in Omniverse.
GTC 2021 was a beast. There were over 100 slides that the team and I worked on, and it was a lot.
Because of the type of information that we get, everything is super technical. We have charts, we have images, we have systems, we have a whole bunch of things that we need to fit normally on one slide that needs to make sense to the audience. So it's almost like solving a Rubik's Cube, where it's an extremely complicated problem that we have to solve. How can we visually tell this story and make it interesting for the audience? Once we get the slide figured out and figured out what we want to say, that's where we bring in the 3D team and start creating mock-ups for them. And mock-ups can range from Photoshop to PowerPoint to kind of getting the general visual idea.
When I first joined NVIDIA, we were still using CPU rendering, and each render would take quite a long time to finish. And this year, we full-on went into Omniverse. So everything in the keynote was created in Omniverse using the real-time engine. And that allowed us to quickly make changes.
We started Omniverse knowing full well that we're not going to be able to build the metaverse ourselves. There are already great tools out there that people use every day in every industry that we want people to continue using. Omniverse was built with the idea that we can take these existing tools and new ones that will come into the future and augment them with our technologies.
I would prepare my assets still in Maya, but then I would export it out and I would do the layout in Omniverse. It's quicker because you see in the viewport right away the shaded view with the lighting interaction, and it's very speedy. Content changes come pretty frequently. I created all these different panel templates that they can just use and insert the content. And it really helped us to deal with the amount of work that was coming down the pipeline.
We went through probably 50 different iterations for the template that we used, and it ended up being something really beautiful.
One of the biggest challenges we faced with the slides were very large panels that sat behind the hardware. And those panels were made of this black lacquer, piano lacquer, that were super, super shiny. So anything that you placed anywhere near it, it would completely reflect it. We had to be very, very careful about where we placed those lights.
Another slide that we had a challenge with is the whole idea behind Omniverse itself. It's very, very difficult to take all of the information of how Omniverse works and the apps that it uses and the collaboration and everything and show that visually on a slide. For the nucleus part of the Omniverse slide, I think that alone was 15 different variations.
Because it's so fast and interactive, you can hop on a Teams meeting or a Zoom call with a designer and have them watch you, and they can make changes on the fly.
What if you move like more to the right so then more of the card is lit up?
Okay, sure.
And then you're able to ask all the questions you want at once and see the results, compared to almost having to work on pieces by themselves because you can't do the whole thing at once because it's that many more emails and iterations. We had 2 slides in the deck that were icons and text, and that's it. You have to find the balance between, okay, this looks elegant, but does it look 3-dimensional? And that was kind of a struggle that we went back and forth on.
The designers for the slide wanted to bring those icons into the 3D world. So I was able to do the geometry in Houdini, export it into Maya, and once I was able to have the 3D geometry, I was able to apply my MDLs, this really nice, beautiful gold material, to those icons and then port them over to Omniverse and have them live in a very real environment. So they're reflecting on the floor, they're reflecting anything that's beside it. And because Omniverse is, once again, so blisteringly fast, I was able to get feedback from the designers.
It was definitely one of our big line art challenges that we didn't think was going to be as complicated because it's just icons, but the end result looked really, really beautiful.
There's like this triad, this triangle. You have the model, you have the materials, and you have the lighting. When all three of those elements are in sync, you get a beautiful render. They marry so well in Omniverse because of the MDLs.
MDL, our material definition language, which we've been investing in for the better part of a decade, is a big part of Omniverse. Every aspect of physics that affects matter should be described in a material. They're all part of the super definition of a material.
So materials for this particular GTC Keynote was crucial that they all look photorealistic, that when you have a diffused material, it looks like a diffused material. When you have a highly reflective material, it looks just like that. And it's beautiful, especially when you're really trying to highlight the materials that the industrial design team have worked tirelessly over.
The goal of the DGX station animation is to celebrate our industrial design team and their amazing work. Unfortunately, we only had 3 weeks to go from a detailed CAD model to a beautiful cinematic.
We had several people working with me to develop the look and feel of the animation, the lighting, camera angles, and such. We have only so much time to build, refine, iterate. So we set up the entire scene within Omniverse. Omniverse allowed me to make changes fairly quickly, either in Maya or in Omniverse directly. We just bring in the props from Maya through the Omniverse converter and place the lights according to the needs, the look, and the feel of the project. The CAD file was already prepped before this animation. We spent about a day taking the DGX station and converting it over to Omniverse MDLs. Building out the environment took roughly 3 to 4 days. All in all, that process normally takes about a week, taking the CAD file to a usable model and then about a day or two to get the shaders applied and then rigged up for animation. With an animation like this, moving a light just a little bit has a huge impact, and then being able to see that impact through the entire animation is really advantageous. With other packages, I would have to set up the scene, compose lighting for what I would assume would be correct, then render out a frame, wait 10-15 minutes, and then get a result, and then adjust lighting accordingly. Omniverse last year wasn't as stable as it is now. It's gotten better because of the feedback we've had with the Omniverse team, the ability to insert features specifically for our team. During development, we ran into a bug where the motion blur wasn't working the way we expected it to. The deadline was coming up quick within the next couple of days, so we reached out to the Omniverse team.
A few of us made some suggestions. I made a suggestion to Nacho on how we can do a quick hack that would get us actually extremely high quality motion blur. It's typically not done this way because the rendering is slower when you do it, but our renderer is so fast and it's so accelerated that we could afford that. And it actually gives you a better quality motion blur. Nacho hacked that in to the renderer as a Python script in an hour or two, and it's still there.
Start to finish, it was roughly 3 weeks. It was a real crunch all the way through. You have a certain set amount of time, so it'll always be delivered in that time, but the quality is what you end up sacrificing. You have to start rendering sooner, so you have to make compromises as far as look and feel and not have as much refinement. And in this case, we were able to use 10 machines to render the entire animation overnight.
So not only did we show off our photorealistic materials and lighting at this year's GTC, but we also highlighted our highly accurate real-time physics engine, PhysX. PhysX actually predates NVIDIA's acquisition of a company called Aegea. And with it, we got one of the world's finest teams writing physics simulators for real time. The primary focus of PhysX was to accelerate physics inside video games. But a few years back, it started becoming clear to us that the value of real-time high-performance physics is now more than just video games. We were starting to enter markets like robotics and autonomous vehicles. And with PhysX 5, the latest version of PhysX that we have that's integrated into Omniverse, we've been adding high-performance simulations for different aspects of physics that generally we don't see in real time.
In this year's GTC, we show all this amazing demo with all the physics technology, such as fluid dynamics, amazing FEM soft body simulation, and the highly accurate articulation system for robotic simulation and large-scale rigid body simulation in the GPU Accelerate platform. My favorite one will be the skeleton hand, picking up the cup, moving the liquid into one cup to the others. And the reason why I love that demo so much is because it's extremely challenging to simulate those scenes in real time. So for example, in this scene, what we're looking at is we have an articulate skeleton hand, and then each hand has a 5 fingertip, and each fingertip is a FEM-based soft body simulation. So we're using the constraint system and attach those fingertips into the rigid body, and using friction to lift up the cup. Each fingertip has a 6,000 tetrahedra, and inside the cup, that is our particle system TED. Just in that small amount of water, it actually has a 20,000 particles inside. Basically, why we are making this demo, it made us realize a lot of technical detail we have to address. For example, the fluid dynamic, because the particle is such a tiny particle, it's hard to make it stable in a cup. So normally, when you're doing the particle simulation, right, even though the particle, the simulation is not stable, which is mean the particle jumping around, but you can hide it by using a nice render on top of it. However, in that scene, we don't have a proper render in there. So if the particle is not stable, you will see like a bubbling effect in there, but you see the particle is extremely smooth. So during the process of making this demo, we actually improve our fundamental tech dramatically.
Physics to us is extremely important. We've had a renewed effort to not only make our physics extremely fast, but also make it extremely accurate. With games, accuracy and fidelity is not as important. But for tasks like robotics and training AIs, the fidelity is extremely important if the AI brain that we're building to put inside these robots learn physics in a world where physics works differently or incorrectly, not like the real one, they're not likely to be successful once we move their brains into the real world. When building modern factories, robotics are an essential element of the design. But the only way to really know that your design is correct is to test it out. And the only way to test it out today is to actually build it and then try it. With a digital twin, you get to make those design decisions very early in the process and have many iterations when it's still inexpensive and safe to do.
What we demonstrated, along with BMW, was a vision for the factory of the future, where we believe the tools and the workflows, the data, everything will be streamlined by connecting it all to our Omniverse platform. We are able to bring significant improvement in efficiency of the factory design, optimization, and operation.
The BMW Factory of the Future is a real-life plant located in Regensburg, Germany. This factory is gigantic. It's a monster. It's 600,000 square feet, and it's just packed to the gills with stuff. 2 billion triangles, roughly. There's tens of thousands of objects. There's thousands of materials, and all those materials are all PBR with multiple textures. There's hundreds of full-resolution cars and slings. There's 120 digital humans doing their digital human thing. There's autonomous robots learning about their environment, becoming optimal at what they do. Then there's a whole other section of robots that is being driven by data from the factory. No animation happening to their articulation. It's all just being fed straight from the factory into Omniverse. So data starts in its CAD package just like usual. You send it into Omniverse, and then as updates happen in the CAD package, Those updates are just sent into Omniverse, and it's not like the whole thing has to come over every time. It's just the differences that are sent at that point. So Omniverse has the capability to ingest E57 format point clouds, and it does it on the fly. So BMW was able to provide us E57s, and we just simply dropped that into Omniverse, and then we went through the process of updating, creating real-time lighting, creating real-time materials and textures to create a one-to-one digital twin of the actual factory, both in fidelity and behavior. And materials play a heroic role in that. NVIDIA's physically accurate MDL programmable shaders are purpose-built to represent the real world. For robots, in order for them to understand the world, that world really needs to be represented in a physically accurate way. And it goes way beyond form. Just because you have a good-looking 3D model really doesn't tell the robot anything. It needs to know color, reflectivity, roughness, meltiness, light emission, subsurface scattering. They all play crucial roles in the identification and the validation of proper materials of any given object or work set.
Traditionally, when we talk about materials, normally we're referring to the simulation of the physics of light and matter. But materials actually extend past that. We also want to simulate other aspects of physics, like sound and how it interacts with the materials in a building like this. So material definitions also apply to other domains outside of the visual spectrum.
People are really at the core of assembling a car. The way it works is that there are a bunch of stations along a line, and every station is responsible for putting things like the muffler or some other car part. So it matters how far they are from the thing, what tools they have to use to secure it. Being able to simulate those movements in the context of the digital factory. We had an Extend suit on. I was here in my living room. I was streaming that out through Motion Builder, which was connected live into Omniverse. And all of a sudden, I'm in the world and I'm able to say, okay, I'm having to lean over too far and there's too much strain on my back, and maybe that should be up here. And the order of the materials matters too. So being able to just simulate that over and over again till you really get the right process, it's a complete game changer. There are quite a few sleepless nights on this one. All those nights were always filled with a lot of laughter and camaraderie and making jokes, and it actually worked. So that was pretty fantastic.
Factories are moving towards mass customization. Gone are the days where the lines would just spin out same widgets. Now, consumer preferences are changing and consumers are demanding more and more custom designed products, but it's at scale. So the factories have to be highly reconfigurable. When a company like BMW has to rapidly reconfigure a factory line to manufacture a new line of cars, they have to keep in mind all these different optimizations of sequencing, timing, and the shortest path from point A to point B, the intralogistics. And these intralogistics are fulfilled by robots. So all this needs to be simulated before you reconfigure the factories. And that's where the digital twin in Omniverse would come into play. So you're able to quickly reconfigure the factories, find the most optimal configuration to produce the new line of cars, and then you go about designing it in the real world, and then you operate the factory.
DriveSim contains essentially a digital twin of certain parts of the world. We're taking certain areas, certain cities, and creating a virtual world that's a facsimile of the real one, where we can test our AIs that we're building to put inside these cars.
In order to create environments in DriveSim, we usually have two ways. One is the manual approach, and the other one is creating an environment from scanned data. So for GTC, we actually went with the manual approach. We first identified the entire Stuttgart route near Daimler facility. We identified 2 key locations, and for those locations, we downloaded the reference data, all the high-res aerial imagery and digital elevation model data. And then we used a third-party tool called MathWorks Roadrunner, loaded those data into that tool, and created an environment. So we built the road network, we built the terrain. What we have in Omniverse is we have a MathWorks Roadrunner importer that allows us to import that entire environment in one shot And when you ingest that entire environment, we do a lot of processing on the Omniverse side to make it very photorealistic. We replace certain assets with high-resolution models. We optimize many areas of the scene for ray tracing. We also enable randomization for synthetic data generation and also for testing drive behaviors, not just for camera, it's for multiple sensors such as LiDAR and radar. So a couple of challenges that we faced to create the environment for GTC. We have a large tunnel to build, and it was super difficult to get it right. So we had to drive within the tunnel, get lots of images, reference images or videos to see how the tunnel exactly looks from inside. And then we took all that information and then we had to model that tunnel from scratch. We went through the texturing, and the ray tracing engine did an excellent job in simulating all the bounce lighting. All the lights bounced within the tunnel, gave that global illumination. The sunlight was hitting just the right amount and illuminating the entrance and the exits of the tunnel. So it turned out quite well, but it was one of the challenges that we overcame.
The biggest challenge that we have worked with when working with the DriveSim folks is really meeting the performance needs that they have. A really important aspect of this is that we're using DriveSim to train these sensors, and we have to depict an accurate version of the world. The sensors have to believe that they're actually in the real world, so the accuracy of the lighting and the accuracy of LiDAR and radar have to be correct. When we're making DriveSim, it's really important to be able to make these really beautiful ray-traced images and to be able to do that in high performance. And so we build up high-performance representations of the scene that are very GPU-friendly. So when you have a Mercedes driving down the street, we also have little programs that are controlling the cars that tell them how fast to go and whether they need to turn left or right or stop at that stoplight. Then we feed that into physics, and then physics does the actual simulation of the vehicle and the response of the suspension. What should the wheel angle be? What should the wheel torques and brake torques be? We pull those results back, and then we feed those to the renderer so that we have accurate physical response. And so one of the things that's tricky here is because the DriveSim main loop has to be running at a really high frame rate, you have to be able to have the physics interaction happening and our other interaction happening, and we do that by having these things be asynchronous. I remember, I forget, this was maybe like 3 weeks out from when we needed to deliver recording, and we went up to record and the vehicles would all move, but their wheels all stay behind. It was fun to watch, but yeah, we fixed that bug.
Now, with this kind of accuracy, we could generate all the synthetic data with various kinds of lighting and randomization in place. And we proved that it works by using these training data and deploying it. And we saw the Eagle car could drive from point A to point B all by itself. It was all using training data generated from Omniverse for GTC.
The Factory of the Future and DriveSim demos really shows NVIDIA's passion for pushing ourselves to the limits. But we didn't stop there. Jensen challenged us to create a digital twin of his kitchen and also himself to be featured in the pivotal moment of the keynote. This kind of undertaking is the epitome of what GTC is. It combines everything that NVIDIA does in computer graphics, AI, and simulation. In order to pull this off, our creative engineering and research teams all had to work together as one.
Prior to COVID, NVIDIA was putting on large events and keynotes with Jensen on a stage in front of a large audience. Once COVID hit, we had to rethink what those keynotes would be.
Welcome to NVIDIA GTC 2020, our first kitchen keynote.
So Jensen challenged us to find ways to elevate his kitchen keynote. So we went off and created a 3D digital twin of his kitchen that we could find unique ways of bringing his kitchen to life. We took hundreds of photographs from every angle of his kitchen, pumped all of those photos through a photogrammetry application that would build a coarse model to scale. And that became the starting point in which our modelers would add a lot more detail and accuracy to the model. The kitchen is very complex. If you look closely, you're going to see like thousands of screws, a lot of hidden objects in the scene that are actually the fabricated components of the kitchen. I would say there's probably 6,000 to 8,000 objects in the scene, polygon-wise in the hundreds of millions. There are a few little Easter eggs that we put in there. There's a coffee grinder with an NVIDIA logo on it. The olive oil tin, the name was changed to Tau, which is one of the software products that we announced. And somewhere around there, a Lego Jensen's running around. So as part of the keynote, not only did we virtualize the kitchen, but Jensen challenged us with virtualizing himself. You'll see the kitchen disassemble, and when Jensen reappears inside of the holodeck, it's actually the virtual version of himself. He proceeds to introduce our new CPU, teleports away, and then the next time we cut back, we're back to the real Jensen.
I've been in visual effects for over 20 years, so creating a digital replica of somebody real is something I'm quite familiar with. But in this case, it's a little different. Unlike a film, we're able to capture as much data as possible of this person. We have a very minimal set, and everything else had to be done through AI to synthesize. We've been developing a lot of AI-based generation, animation, rendering technology, and that was the big push to see how far our technology can do with very minimal data of Jensen. We do need some scan of Jensen, a 3D scan.
We found a service that had a large truck, and inside the back of the truck were hundreds of DSLR cameras. We pulled that up to Jensen's house. He stepped into the back of the truck.
All right, what's the game plan? And 3, 2, 1. Nice, you can relax. How was it? It hurt just a little.
In a series of poses, took thousands of photos of him, and that was the base in which we constructed the 3D model. So once we had the model of Jensen, now we have to bring him to life. Two main components to bring him to life was the facial performance and the body performance. The facial performance was driven by our technology audio to face.
The beige hue on the waters of the lock impressed all.
An automated way of using an audio clip to drive the facial performance of any likeness character. And that returned a pretty good result, but it wasn't pixel perfect and it wasn't photoreal. We then reached out to the video research team. They were working on a technology called face video to video. And what that would do is that would take a photograph of Jensen and map it to the animated CG version of himself. This vid-to-vid technology enabled us to bridge that uncanny valley from the CG model to a photorealistic, convincing version of himself full screen on camera.
Kevin is like the director. He planned the whole video shootings and the scene and where Jensen should be. Simon's scene is more like the main actor. They create a CG model of Jensen and to do the performance, acting, talking. And our team is more like the makeup man. We use AI to put fancy makeup on top of the CG Jensen to make it realistic. One challenge in render face, especially under the holodeck environment, is that a strong specular highlight on the forehead. To have a realistic rendering, the specular highlight should remain in the right position. It shouldn't rotate with Jensen. And this is a deep learning method. You don't have the physics to control how it looks like. We create room where the lighting is similar to the holodeck in our final CG world. And we have Jensen stay there and we take a couple of videos, and it was about 3-4 days before the keynote, and we are able to quickly leverage the data to fine-tune our model and achieve better illumination control.
So bringing the face to life is just half of the battle. The body needs to reflect the vocal performance as well. So we were working on another technology called audio to gesture.
Amazing increase in system and memory bandwidth, the basic building block of the modern data center.
What this does is take the same audio input and output gestural qualities that are reflected in what he's actually saying. In order to do this, we hired an actor to learn Jensen's physicality by studying past keynote events. We had him get into a motion capture suit, record 8 hours of him reading past transcripts of Jensen keynotes, at the same time physically mimicking Jensen's performances. That 8 hours became the training set that would be driven by Jensen's unique audio delivery for the current keynote.
Now you actually just can provide a voice and it'll have body motion. We had so many variety of Jensen to pick from. We had a 21 version, and each time we do an update, there's 21 of them to choose from in different varying performance. It was actually getting to the point where I'm actually casting, because they were all performing well.
The performance will be loaded to CG Jensen's model to create the CG shots. And we take the video and turn the face part into realistic Jensen. The face part is then composed with the CG shots, and the final Jensen, including head and body, is put into the kitchen to complete the final production of digital Jensen. As an AI researcher, I come from a machine learning background, and I was not familiar with the movie production pipeline. An important thing for me is to feel the pain. How difficult it is to produce the digital human, and to kind of challenge myself how we can create tools to make digital human production a much easier process.
The virtual kitchen and virtual Jensen presentation was done in Omniverse, along with many other applications that help create the textures, some of the modeling as well. And that's the beauty of Omniverse. It's a collaboration simulation platform that enables us to work multi-directionally across all these applications, while we can build and develop custom technologies very quickly, especially AI-based technologies, which there isn't many platforms we can do that on today.
The beautiful thing about Omniverse is you don't have to give up those apps that you've known and loved. I still use Maya, I still use Houdini and Substance as well, but I'm also using something that can make it really, really fast to get beautiful results in almost no time.
To me personally, I feel the quality has increased and we moved into the photorealistic phase of look and feel.
The RTX renderer inside of Omniverse allows us to do real-time ray tracing in a way that I haven't seen in other things on the market. So I feel like the ability to be able to control our destiny with Omniverse and be able to build it to be something specific for what they need, I think gives us a lot of power.
We built Omniverse first and foremost for ourselves here at NVIDIA. We built it for our simulators, for autonomous vehicles and robotics, but also for our creative team. We started Omniverse with the idea of connecting existing tools that do 3D things together to build a sort of what we're now calling the Metaverse. We spend a lot of energy and time and blood, sweat, and tears to present it in the best light possible. If we do our jobs right and we build something as great as we believe it is, then I believe 20 years from now, we're still going to be using it, but it's going to be much more evolved. With so much groundbreaking stuff here at GTC 21, I really can't wait to see what the team does next year.